In the last few videos, we've been looking at sequences of functions, the notion of pointwise convergence and uniform convergence. And here we want to prove an important result involving uniform convergence. But before we do that, I want to recall a couple of definitions. So let's suppose that f sub n is a sequence of functions, all whose domain is A, which is a subset of the real numbers. So in other words, f sub n is a function from A to R. We say that f sub n converges to f pointwise on A if, for all x in A, the limit as n goes to infinity of f sub n of x equals f of x. So notice at this stage right here, this is just a limit of a sequence of numbers because we fixed this x up here. And if you were to write down the epsilon n definition, you would notice that the capital N would have the possibility of depending on the x value, which we don't want to happen for this notion of uniform convergence. And then I also want to notice that we did some examples in previous videos that showed that this pointwise convergence does not necessarily preserve continuity or differentiability or other nice characteristics of the functions. So in other words, we could have a sequence of functions f sub n, all of which are continuous, but they converge pointwise to a discontinuous function. Or maybe they're all differentiable, but they converge pointwise to a function which is non-differentiable. Okay, then next we say that f sub n converges to f uniformly if given epsilon bigger than 0, there is an n in the natural numbers such that this f sub n of x minus f of x in absolute values is less than epsilon, and this is true for all n bigger than n and x in A. So in other words, this capital N only depends on epsilon, it does not depend on x. So in other words, the cutoff point to get you within epsilon of the value of f of x does not depend on the actual value of x here. It only depends on how far into the sequence you want to go. Okay, good. So here's the first theorem that we're going to prove. That says that if we've got a sequence of functions f sub n, and those go from A to R, and they are continuous at a point A, and we have uniform convergence to this function f, then that function f is continuous at A. So in other words, all of these nice conditions that are not necessarily preserved under pointwise convergence, well, at least continuity is preserved under uniform convergence. And we'll check in on the other properties in subsequent videos. Okay, so let's go ahead and look at the proof of this. Okay, so let's say that we are given epsilon bigger than 0. So I want to use the uniform convergence, so using uniform convergence of the sequence fn, let's go ahead and find maybe a capital N in n such that if little n is bigger than or equal to capital N, we have the absolute value of f sub little n of x minus f of x is less than epsilon, and actually I'm going to make it as epsilon over 3, and you'll see why that's important for our calculation as we move forward. Okay, and I maybe want to say in particular, this is going to be true for little n equals capital N. So let's maybe go ahead and write that down. So we've got this specific case, so f sub n of x minus f of x is less than epsilon over 3. Another thing I want to do is notice that this is true for all x in A. So this is going to be true for any of those x values. That's the big point of uniform convergence here. Okay, so next I want to use the result of the continuity of all of these functions f sub n. And so that's going to allow me to find some sort of delta so that if x is within delta of A, then something else happens. So let's go ahead and do that. So let's find a delta bigger than 0 such that if absolute value of x minus A is less than delta, in other words, x is within delta of A, we have the absolute value of f sub capital N of x minus f sub capital N of a is less than, and I'm going to make this epsilon over 3 again. Again, we'll see why this is necessary in the calculation. Okay, good. And how did I do this? I used the continuity of f sub capital N. And I guess I should say continuity at A. And now I want to go ahead and make my final calculation, which will really involve just like adding 0 a couple of times. So let's go ahead and suppose that we have x minus a is less than delta. And what we want to end up with, or what we want to show, is that the absolute value of f of x minus f of a is less than epsilon. That's what would tell us that this function f was indeed continuous. Okay, so let's go ahead and do that. So we've got the absolute value of f of x minus f of a. So that's going to be equal to another thing, which is essentially the same as this with 0 added a few different ways. So I'm going to write this as the capital F of x, and then I'm going to have minus f sub capital N of x plus f sub capital N of x. And so let's maybe motivate why we did that. So we did that because we have control over this object right here. We know that if we apply like the triangle inequality, maybe we can rip this out into an absolute value by itself, and then we can apply this thing that's in peach chalk. But then we've picked up this f sub capital N of x, which is positive, so maybe we want to add and subtract the same thing again. And what are we going to do in that case? Maybe we'll do minus f sub n of a plus f sub n of a. Okay, good. And then again, we can take care of this by the continuity of f sub capital N, which is right up here. Great. But then we've got one last term, and that's this minus f of a. So minus f of a, and then that's in absolute values. So I want to point out that I have control over this stuff that I am underlining in blue by the uniform convergence of our sequence of functions. In particular, this thing right here, which holds for all x values. And that also controls the size of this thing, which I just underlined in pink. Because again, that's true for all values of x in A, including x equals little a. And then finally, I have control over this thing that I'm underlining in yellow by the continuity of f sub capital N. But now I can go ahead and apply the triangle inequality to this. That's going to give me something that is bigger than or equal to. So this is going to be less than or equal to, well, essentially all of this split up with these different colored underlined things. So this is going to be f of x minus f sub n of x plus absolute value f sub n of x minus f sub n of a, and then plus absolute value of f sub n of a minus f of a. But now notice by our construction above, we have this part is bound above by epsilon over 3. This part is also bound above by epsilon over 3. And this third part is bound above by epsilon over 3. So that means this whole thing is bound above by 3 times epsilon over 3, or epsilon. So now looking at the extreme left and right hand side of our inequality, we see that we have arrived at the inequality necessary to show that f of x, or the function f, is continuous at A. Okay, this is called the Cauchy Criterion, and it should look pretty similar to the Koshi Criterion for showing that sequences converge, sequences of numbers, I should say. And it goes like this. F sub n converges to f uniformly on A if and only if, for all epsilon bigger than 0, there is a capital N, which is a natural number, such that if little m and little n are bigger than or equal to this capital N, then the absolute value of f sub m of x minus f sub n of x is less than epsilon, and that has to be true for all x in A. So this is helpful because at times it may be hard to compare these functions fn with this function f, but it's easier to compare these functions fn with themselves with just a different index. Okay, so let's maybe do this forward direction first. So in other words, we're going to suppose that we have uniform convergence. So let's go ahead and do that. So let's suppose that fn converges to f uniformly on A. Great. Now let's maybe look at this and see that we need something to be true for all epsilon bigger than 0. So that means we need to say that we are given some arbitrary epsilon bigger than 0. And then next, let's go ahead and pick a natural number n such that if little n is bigger than or equal to capital N, we have the absolute value of f of x minus f sub little n of x is less than epsilon over 2. You can maybe see that this is gonna go kind of the same way that the proof for the Cauchy criterion of sequences of numbers works, involving the triangle inequality and adding 0 and stuff like that. Good. So now let's go ahead and launch into the part of this then statement. Okay, so let's suppose that little m and little n is bigger than or equal to capital N, and we want to consider the object f sub little m of x minus f sub little n of x. Great. So now I'm going to add 0 to this, but I'm going to add 0 in the form of f of x minus f of x. So that's going to give me f sub little m of x minus f of x plus f of x minus f sub little n of x. But that's super helpful because these two objects, we can control their size, and we can control their size because we have this uniform convergence up here. So now using the triangle inequality, we can split this apart into two inequalities. So that's going to give us the absolute value of f of x minus f sub m of x. So notice I just move that around as well, or I guess I switched the order of subtraction. That's an absolute value, so that's no big deal. And then I've got plus absolute value of f of x minus f sub n of x. But now, given that little m and little n are both bigger than or equal to capital N, we know each of these parts is strictly less than epsilon over 2. So here we've got this is less than epsilon over 2 plus epsilon over 2, but that's going to be equal to epsilon. But now looking at the extreme left and right hand side of the inequality, we see that we have arrived at the conclusion of the right hand side of this implication. Okay, so let's maybe get rid of this proof and we'll do the reverse direction. Okay, now we're ready to look at the reverse direction of this proof. So the tricky part here is that we first have to construct a function for which our sequence will converge uniformly to. Okay, so let's maybe see if we can do that. So let's notice that the right-hand side of this implication is essentially the Cauchy criterion for sequences of numbers. If we look at this as a sequence of numbers f sub m evaluated at x, it's just we've got a sequence of numbers for every x in A. So that's going to help us get our candidate for the function. Okay, so let's go ahead and see if we can spell this out. So notice for all x in A, we have the sequence of numbers f sub n of x is a Cauchy sequence in R. Great. So, but a Cauchy sequence in R means that it converges. And what does it converge to? Well, we might as well call the number that each of these converge to f of x. So let's define the value of this convergence, like I said, to be f of x. So the limit as n goes to infinity of f sub n of x equals f of x. Okay, so just to reiterate, we're viewing this as a sequence of numbers for all x in A. We know that that's a Cauchy sequence by our assumption here. That means it converges because we know a sequence of numbers converges if and only if it is Cauchy. So that means that this has a defined limit, and so we're gonna set that limit equal to f of x. And notice that this defines a function, and that function is a function that we will call f from a to r. So you might say, okay, well, how do we find the values of f? Well, we find them by these limits right here. Okay, good. And now all we have to do is prove the following claim, that f sub n converges to f uniformly on a. Good. Okay, so let's see how we can do that. So let's say that we are given some epsilon bigger than 0. And so let's go ahead and point out what we want to show is that the absolute value of f of x minus f sub n of x is less than epsilon, and this needs to be true for all x in A. Great. Okay, so now let's go ahead and find a capital N, which is a natural number, such that if little m and little n are bigger than or equal to capital N, we have f sub little m of x minus f sub little n of x are within epsilon of each other. Okay, so that's possible because we have assumed this Cauchy criterion. I should say this right-hand side of this thing, and that's going to be true for all x in A. Okay, good. Now what we're going to do is look at this object, so absolute value of f of x minus f sub n x, where this little n is bigger than this capital N. Good. And now I want to notice that this f of x can be written as this sort of limit. I'm going to use m in this case. So let's go ahead and write this as the absolute value of the limit as m goes to infinity of f sub m of x minus f sub n of x. Great. But next, I can bring that limit out of the absolute value because this absolute value is like a continuous type function. So that gives me this limit as m goes to infinity of f sub m of x minus f sub n of x, and that is in absolute values. So notice this n is fixed. So I guess let's maybe clear that up here. So fix n bigger than or equal to capital N. Good. So like I said, this little n is fixed, but this little m is limiting. Okay, good. But now, because of this setup, we know that since m is going to go to infinity, at some point it will be bigger than this capital N, and that's all that really matters for the limit. So that means this limit is going to be less than the limit as m goes to infinity of epsilon. And so that's because we can replace this thing in absolute values just with epsilon. Because again, at some point, since m is going to infinity, it's going to surpass this capital N here. But once it surpasses that capital N, we know that the difference of these two things is less than epsilon. But notice that's taking the limit of a constant epsilon. So we have this is equal to epsilon. So now notice underlining this part and this part is exactly what we wanted to show to finish this direction off. And that's a good place to stop.